This chapter is on household wiring, but before the power comes to our house, how is it transmitted from the generating station, and what is the use of step up and step down transformers? This is for an efficient transmission of the power into your house. And then we will see the two systems of wiring in the house, the tree and ring systems. Each has its advantages and disadvantages. And then what are the components of wiring system, switches, fuses, etc. And finally, the safety device thing. Welcome to the portals of real learning. Don't skip and listen carefully right till the end. In this concluding session, let's learn about power transmission from the generating point to the consuming point, and then distribution of that power in households. Power is generated at a power generating plant, and then it has to be transported over a very long distance. So a typical diagram can be like this, that you have the generating station, and then these towers are there where cables are installed. Those are called transmission lines. And then reaching the consumer's city, then various wires are drawn out to all kinds of consumers, industrial consumers, household consumers, etc. But the thing is this, that when we have to send it over long distances, we have to use something called a transformer in order to minimize the heating loss. Now, one very interesting thing, guys, is we say Ohm's law V equal to IR. Through a given resistor, if you increase the voltage, the current will increase. Now I'm saying if you increase the voltage, current will decrease. Because in the case of this Ohm's law, we are not doubting the power generating capability of the battery. We are assuming that the battery can give us whatever power we need. But in a power generating plant, it is fixed 100 megawatt, 500 megawatt, whatever. So voltage into current is a constant. That is the power generated, right? If you increase the voltage, current will reduce. And the heating loss is I square R always. We can't avoid the resistance of the transmission line, obviously. If we can reduce the current, then the joule heating or transmission losses are minimized. And raising this voltage is done by a device called transformer. It can raise the voltage, it can reduce the voltage. So the typical method is that at the generating station, we have, let us say, 400 watts of power being generated, and let us say at a voltage difference of 400 volts. So this must be stepped up to 33,000 volts and then sent over very long transmission lines. And then while coming back to the consumer, this must be dropped back to 220 volts, because in our homes we are supposed to get 220 volts. So throughout the long transmission line, the voltage must be high so that the current is low, so that the joule heating is low. That is the job of a transformer. Now let us say it has come from our, so many transformers are there, which is called the city substation. From there it is coming into a house. Now it has to be distributed. This is not a DC circuit, it is called an AC circuit. So there is no positive or negative here. In AC, the current direction goes up and down, the direction reverses. The frequency is 50 hertz, so 100 times a second, the current direction reverses. So wherever the current is coming from is called the live wire. The live wire is usually shown in red, sometimes in brown. This is where the power is actually coming in. So it comes in and it goes into an appliance, and then for a current there must be a return path. So the neutral wire is painted black, and that is neutral is just the return path, nothing else. Live is where the power comes from. Neutral is where the current goes back, the return path. The third wire called earth, usually green, and that is for safety purposes. That is not connected as such to any live or neutral, certainly not connected. It is connected to the metallic body of high power appliances so that any risks of electrocution, etc., are avoided. And that green wire is also connected into the earth deep below, and we'll show you the earthing pits. The symbol is this. All right. So, live wire, the current will enter from the city substation. There's something called a fuse wire. It is shown like that. It has got a rating, say 5 ampere, 15 ampere, 30 ampere. Due to the heating effect, it is designed in such a precise manner that if the current exceeds that value, it will melt, simply melt, and the circuit will be broken and the current will stop. So, fuse is a protective device. It works on the principle of the heating effect. So, just to protect the house, there's a fuse kept at the pole itself, company or pole fuse, and that is usually of the order of large 50 amperes or so. And then immediately a meter is put, that is a kWh meter, so that whatever you're consuming can be recorded. You got to pay for it. And then these live neutral earth wires are coming out from that meter and they go to the distribution board. From there, wires are drawn out into the various parts of the house. Then in the live wire itself, you put another main fuse that is usually 15 amperes because this is coming from the company, from the pole. From this pole, he may be serving many houses. That is why 50 amperes. But in your house, you need only 15 amperes, and that is how it goes. And there's a switch here, which is double pole switch like this, which simultaneously connects live and neutral. Okay. So all live, neutral, and earth go into that switch. And then these three wires go into the various rooms. The neutral and earth, the neutral and earth are shorted at the substation itself. Shorted means there'll be no voltage difference between them. So that the neutral, anything that you earth is taken to be at zero voltage. And if you short the neutral, that is also at 0 volt to start with. Now, there are two methods to distribute this in a house. It is coming into the distribution board, as we saw, the live, neutral, and earth. So live can be brown or neutral can be blue. Earth is always green. The usual thing is the live is painted red, neutral is black, and earth is green. But sometimes live is also painted brown and neutral in blue. Earth is always green. So one is a tree system. So this live neutral earth came, and then the fuse, please note, is always connected to the live because if the circuit has to break, it must break at the starting point, not at the ending point. What I mean by that is suppose live is coming like this into an appliance, okay, and then the return path is a neutral, right? And you connected a fuse in the neutral part by mistake. Suppose due to some problem, the current drawn is very high and you're operating this appliance, the fuse will blow later and you are still touching it. The fuse should be here so that the supply is cut off right at the live part. So fuse is always connected at the live part and then it goes to room 1, room 2, room 3 just to balance. So all these wires are taken. Live goes, neutral goes. So you can see the blue line goes, the green line goes to all the rooms. And in each room I have shown a bulb or a fan will have only live and neutral. But a socket which is supposed to power High power devices will also have this earth. The earth will be the top one, and the live will be this, and the neutral will be this. So, like that, it is done. So, each branch has a fuse, and load is divided equally. The total load for all the rooms should not exceed the specified value for a house, and the distribution is through parallel circuits to room 1, 2, 3, and each is having its own fuse. But problem is, if one fuse blows, then all the appliances in room 1 will go off until you replace the fuse. That is the problem. And the live wires that are drawn here, they are carrying the current, should be of appropriate current carrying capacity. They should be thick. What do you mean by current carrying capacity? Capacity means that you don't get too much heated up when you're carrying a current. So if you're thick, your cross-section area is large, your mass is large, then the heat capacity is larger, so your temperature doesn't rise all that much. So anything that has got a high heat carrying capacity will be thicker. And high power appliances are earth, like microwave oven or air conditioner. Earth means the metallic body of those appliances are connected directly to the earth, so that the body is at 0 volts. Otherwise, if there's a short circuit or something inside and you happen to touch the body, then you will get a shock because the current will go through your body, and that can be very dangerous. Okay. There are some disadvantages. We require different plugs and sockets of different sizes for various current carrying capacities. Current carrying capacity means thickness. So you will see that for a low power device, that is, if you're connecting a laptop, then your plug is small. The plug socket is small with the 3 holes. But if you're connecting, let us say, an air conditioner, then it is bigger. It has got a higher current carrying capacity. This is a 15 ampere socket. This is a 5 ampere socket. So large current means high load in electrical engineering terms. So for a high load thing, you need to have a high current carrying capacity plug and socket. So it requires different plugs and sockets for different capacities. And as I mentioned, one fuse blown will disconnect all the appliances in that branch. Wiring is expensive. I'll show you how we can reduce the wiring cost in another system called the ring system. And one important limitation is, suppose a new appliance which needs 15 amperes, but all the wiring that you have done is only for 5 amperes. Then you will need to draw a new line completely from the distribution box. That makes it inconvenient and also expensive each time that you have to bring in a new appliance. So we can get rid of some of these problems with the ring system. Instead of a tree, the tree was what? We had the live neutral earth coming to a distribution box, then one branch goes to room 1, another branch goes to room 2, another branch goes to room 3, like a branch of a tree. Here we don't have a tree, we have a ring. You see, we have a ring. This ring is the live ring. Then in between, inside, we have this blue one, which is the neutral ring. Then we have the green ring, which is the earth ring. They're all rings. And from the distribution board, they're all connected appropriately, as you can see, to the ring. And to each bulb or socket, we take up connections, live, earth, neutral, as the case may be. And we can put individual fuses and switches for each one of them, individual fuses and switches for each of those sockets and bulbs. Okay, so that is a ring system. A ring goes all around the house. The main fuse is rated 30 amperes here. But now you see the connection that we are taking. Okay, there's a separate connection from live wire of the ring for each appliance. Separate connection, separate connection. And you can put a fuse and a switch in that line. It gives us flexibility. Fuse of this socket goes off. That doesn't affect other appliances at all. But in the tree system, if one fuse blows, then all the appliances in that room, they go off. Okay. For each appliance, though, we have to take care that the current carrying capacity wires are used, the appropriate wires for that particular current. They should be used. Some advantages: the current has two available paths in a ring. It can go like this in a ring or go like that in a ring, right? In order to travel to an appliance. So one thick wire suffices, and the wire for the main ring is of a lower current carrying capacity than needed for a direct connection to mains. It reduces wiring cost because large current carrying capacity means large thickness, large mass, large cost. It reduces wiring cost. Plugs and sockets can be of the same size. However, the fuse rating should be chosen suitably for various appliances. Very importantly, since the ring is there throughout the house, if you are putting a new appliance, you don't need to draw a completely new wire or something for the distribution box. You simply connect it to the ring, making sure that total load is not exceeded. Each appliance has its own fuse. Okay, so those are the advantages of the ring system. So let's talk about the fuse a little bit. Basically, a safety device. The traditional one was a wire of a low melting point and high resistivity which melts. Okay? It's a safety device to limit the current and to prevent fires, to prevent overheating, and usually made of lead and tin, an alloy of lead and tin. Copper is not used because it has got a high melting point. We need it to melt immediately, right? It is always, the fuse is always connected to the live wire before the appliance. If there's any problem, then the supply should be cut off before it reaches the appliance, not afterwards. These are the kind of plugs you will see. If you pull it out, then you'll see there's a fuse wire. Or you will see this kind of a fuse wire inside a casing or like this. But now there are circuit breakers, miniature circuit breakers. In a fuse wire, when it melts, you have to replace the fuse wire. Here, it breaks. So once you have attended to the problem as to why there was this high load and why the current exceeded the value, first you investigate, rectify that, and then when you want to resume the supply, just bring it back. You don't have to replace any wires. Miniature circuit breakers. But don't ever fiddle with fuse wires or circuit breakers. They are very, very important safety devices. Electricity can be very dangerous if you don't handle it properly. We have seen cases of fire happening in a building due to short circuit. And I'm amazed to hear all these stories. Okay, you have a short circuit, but why did the fuse not blow? Why did the circuit breaker not blow? What was the design of your distribution system? Right? Now, switches, they are just connecting or disconnecting an appliance. The usual switch that you see, tuck, tuck, your door is like the single pole switch. It disconnects only the live wire and is connected to the live wire, not to the neutral. The switch should be connected before the appliance, just like the fuse is also connected before the appliance, not afterwards. There are double pole switches also, which disconnects both live as well as neutral. So this is live, this is neutral. You press it, you are establishing the circuit between live and neutral simultaneously. You open it, then the circuit gets broken. It's basically an on-off device. One interesting staircase switch I want to talk about. Have you heard of the staircase switch? The problem is that a person wants to climb up a staircase. He needs a switch here to switch on this bulb. When he reaches here, he wants to switch off the bulb so that it doesn't waste electrical energy. How does it switch off? Again, he has to go down, is it? He must have another switch. From here, he can shut it off. Again, when he's returning, He toggles this switch. Toggle means change the state from here to here. While returning, he should be able to switch it on, and again, while coming back, he should toggle the switch. So both the switches should be toggle types. So what is the wiring there? The switch is different, the wiring is different. Here is a bulb, here is a power source, I'm just showing a battery. And there are two wires like this, and this is switch 1, this is switch 2, right? Right now, the circuit is broken because this is connected to this wire and this is connected to this wire. Current would have started like this, gone like this, but then stuck. All right. So this is at the bottom, right? Imagine this S1 is the bottom switch. So the man is wanting to switch it on, so he toggles it. Toggles means changes the position from here to here. Now what happens? Current will flow like this, like this, like this. Circuit is established. Then he reaches to S2. There he toggles S2. S2 was like this, he toggles it and brings it like this. Now what is happening? S1 is in this position, S2 is in this position. The current, will it flow? Well, it comes like this, comes like this, comes like this, comes like this, but here it stops because S2 is on the other side. While returning, he toggles S2 back, then the circuit is re-established. And when coming down here, he toggles S1 back, the circuit is broken. So that is the staircase switch. So let me just erase this so that you can make a mental note of how this kind of wiring is done for staircase switches. Finally, earthing. There are pictures like this. We make an earthing pit. We dig some 2-3 meter deep. We take a copper rod, which is a very good conductor. Then we put a big copper plate, put charcoal and salt mixture here, put some water also so that there's a good conductivity here. There's a very thick copper plate here. Thick copper plate means large current carrying capacity. And then this from here copper wire is taken to the kWh meter to various appliances. All the high power appliances will have their outer bodies earthed. That is a physical design, and you see there is the actual photo of the earthing pit over here. Symbol is this with 3 lines. This is also used to protect us from lightning. Tall building, lightning can strike, but instead of striking the building, we make some spikes over here, metallic spikes, which tends to attract the lightning. And then we take a thick copper wire and make an earthing pit right down here, separate earthing pit, separate earthing pit. Don't mix it up with this earthing pit. You make a separate earthing pit for lightning arrestor. This is a very important device for tall buildings to prevent lightning strikes. That's earthing. And then you have just 3-pin plugs. As I said, some can be 15 amperes, some can be 5 amperes. Sometimes you have a combination like this. The same plug has got two different kind of holes. One is bigger, one is smaller, 15 amp and 5 amp. Like I showed you, many countries use brown as an indicator for live, blue for neutral, and green for earth, color coding of wires. No loose contact should be there, and don't ever touch with wet hands because normal water is a good conductor. High tension wires means high voltage. So those high tension wires that you have should have low resistance so that they will dissipate less heat. And they should have a very high surface area to whatever heat is being generated should get dissipated fast. And those wires are intertwined, that is for another reason for magnetic effects. In the US, you have different kinds of shapes. In various countries, you have different kinds of shapes also. Safety precautions are required. Avoid overheating. Wires should be of appropriate current carrying capacity. Insulate the wires properly. Connection should be strong, tight fitting, no loose contacts, no loose hanging wires, proper insulation. Electricity is a very good servant if handled well, but can be a monster if you don't take care of precautions. Right? So that completes this chapter. So please go ahead and do the questions from your school textbook and then the assignment that is there on this chapter within the course material. And the next chapter would be magnetic effects of electrical current.